In the year 1750, a man by the name of Gabriel Cramer, a mathematician, discovered a method of solving simultaneous equation in 2 and 3 variables using determinants. He discovered that a simultaneous equation in 2 variables can actually be solved using 3 determinants. He also discovered that solving a simultaneous equation in 3 variables required the use of 4 determinants, which was quite interesting for this man. However, in the year 2022, a Zambian national, Joseph Musonda, standing before the camera here in front, discovered that using ratios, simultaneous equations can actually be solved also using determinants, however different from what Cramer's rule discovered. In this case, Joseph discovered that a simultaneous equation in 2 variables can be solved using 2 determinants. Cramer's actually looked at that is 3 determinants. He also went on to discover that we can also solve simultaneous equations in 3 variables using 3 determinants instead of 4, which Cramer's rule worked on. However, in my methods, there are actually steps that are involved. The first thing is to find the determinants of x, y, and z if it is a 3 variable simultaneous equation. These first solutions are known as the critical values. They are actually substituted in a particular equation again to find the true values. So in today's lesson, I'm going to show you how we can use Musonda's method involving the determinant steps to actually solve the problem of simultaneous equation in 2 variables. As we come next week on a Saturday like this, I'll be also showing you how we can use the determinants to solve actually a simultaneous equation in 3 variables using 3 determinants. Let's look at the question on the board and look at it carefully on how Musonda's method can be applied. We have a problem already here. The first step that I need to make, I need to find the determinants of x and y. So in this case, I don't need to actually find 3 determinants like Cramer's. This is the determinant of x. So to find the determinant of x, I am going to start with 6, negative 15. Then I actually come up with the coefficients of y, which is 4 and negative 3. That will be equal to 6 times negative 3 minus negative 13 times 4, same as 4 times negative 13. And the answer here becomes negative 18 plus, that is positive 52, which gives us positive 34. So determinant of x, that gives us positive 34. Next, I need to find the determinant of y. And to find the determinant of y, I'll have my first column here, coefficients of x. Then the other part, which is supposed to be taken by the coefficients of y, will be taken up by the constants here. 6, negative 13. We find the determinant. 3 multiplied with negative 13 minus 2 multiplied with positive 6. This gives me negative 39 minus, that gives me 12, which gives me negative negative 51. From there, I have to go back to this. X over y must be equal to dx determinant of x over the determinant of y, which is equal to 34 divided by negative 51. We find the highest common factor at that particular point. The highest common factor of 34 and negative 51 is actually positive 17. Our positive 2 here, then our negative 3 there. Remember the first values in the Musonda's method that are found? They are known as the critical values. So our critical value, x is positive 2 and y is equal to negative 3. They need to be scrutinized using either the first equation or we use the second equation. And in this case, a k must be introduced. So we are going to have first equation equals C1. I'm going to have 3x positive 4y. Then my k equals positive 6. It's time to substitute the critical values in this actually equation. I'm going to have 3 multiplied with critical value of x is positive 2, while the critical value of y is negative 3, and now my k here equals positive 6. Substitute what is inside here. We have positive 6 minus 12. Then outside our k equals positive 6. Our negative 6k equals positive 6. I divide throughout by this, and I'll get my k as negative 1. So this value of k must be multiplied with the critical values to find the actual or final solution. So my x is equal to the critical value of x is positive 2. So positive 2 times negative 1 equals negative 2. And my y will be equal to negative 3 times negative 1 equal to positive 3. These are the true solutions for the equation that we have. That marks the end of this example. I need to also appeal to you once more. Should I say not once more? I'll always do this. Kindly share my video, subscribe, and click on the notification button so that every time I post a video, you are notified. Thank you.